All right, guys, we're back and we're looking at fractions. Uh, Trust me, I wanted to go through this topic in the most basic way in terms of just explaining operations, but um, there are a couple of things that I want to talk about, address that might clear things up a bit. I'm hoping give some context, and it's important because what we do in arithmetic with fractions, or when we do later in algebra with algebraic fractions, and you find fractions that you work with throughout math. So it's important for you to be comfortable. But the truth is that we have been using fractions from birth in terms of just the way that you add numbers, and we'll talk about it now. So just a couple of things I want to touch on. The video here will be just really focused on understanding what fractions are, how they work, giving you a contextual framework, and then I'll do another video on the calculation itself. But I want you comfortable with the concept. I have been wrestling with whether or not to discuss this, but I think today's a good day. So let's try to get it done. All right. So in terms of fractions, my first pet peeve and where I'm going to start, I'm hopefully not going to pass like maybe 10 minutes on this video, but I know myself. Let's see how that works. My first pet peeve is that when we talk about fractions, we tend to express them as, parts of a pizza or cake or something like that, which is easy to read on the face of it if I'm talking about a single fraction. So if I say that this is my whole, uh, tempted to say pause there. If this is a whole, yeah, uh-huh. Moving on. And I split that into four parts. Then each of these parts represents a quarter of that total, right? That singular total, that sum, that one, that whole, right? And having said that, it gives us an idea of how fractions work, because what this model tells us is the makeup of a fraction. Essentially, if I were to say that I have in hand two of these pieces here, right? What I have is two, that's my numerator. What you have is your numerator, and the number of parts needed to make that whole complete, that's the denominator, right? This is what we have. Top number numerator represents what you have in hand. The denominator, that bottom number, is saying how many parts were required to make that whole, right? Now, the line here, I'll just add that since we're just drawing labels. This is our fractional line, or our vinculum, which is a term you probably won't ever use again, but hey, we like to know terms. Now, as it relates to fractions, okay, cool. We know that what we have in hand is a numerator, and the denominator represents the total number of parts we need to make one of that thing. Are we used to using fractions? Why do they seem alien to us in a lot of context? And the reason is that we're not looking at how we've just added whole numbers in general. And the fact of the matter is that when you add 2 and 3, and you said to me, brilliantly, that's 5. And I go, oh, congratulations, you can count. It makes sense. Not because we know how to count, but more so because we know that this is 2. What we have is twice as many as the number of parts required to make the whole. And so the denominator here is 1. Likewise, the denominator of 3 is 1. And that's the reason why we can say that the sum is 5 over 1. Because we had 2 parts of a whole that required 1 part to be complete. We had then 3 parts that were added of a whole that also required 1 part to be complete. And because those parts are the same size, we can add them in the same way that I added here. A quarter plus a quarter gave me 2 quarters, right? My English teacher will be mortified. So what I end up with here when I say 2 over 1 plus 3 over 1 is 5 over 1 is fractional addition. And that's how subtraction works as well. Given that the numerator and the denominators are the same, we can just add and given that the denominators for both fractions are the same, we can add the numerators or subtract the numerators. It makes sense because the parts are the same, and so there is no worry that the size of these parts are going to be different and so difficult to add, right? So if I said to you that we have 3/7 minus, let's say, 2/7, you will say to me, hey, the denominators are the same, and so I can subtract numerators, right? If I said to you that we have 4 over 9 plus 2 over 9. You said to me denominators are the same. So, hey, I can add numerator 4 plus 2, 6 over 9, and we're good to go. Whether or not you then proceed to simplify, all right, that's not a problem. We can discuss that at another point, right? So that's the basics of it. We can add, we can subtract, given that the denominators are the same. Okay, that's how fractions work. We'll talk about a little bit more in detail that process when that's not the case, right? But let's make sense of what happens for multiplication, right? Now I have here 2 quarters times a third, right? In essence, I'm trying to find a third of 2 quarters. Now, this is not going to be easy to do. If you had your cake or your pizza and you had your 2 quarters, and then this is your 2 quarters, you'd have to divide that into thirds, right? Right? And a third of that might look like what is over here, right? It's not super intuitive. It's not very straightforward. It won't be super accurate. So there's a process to this, right? There's a way that we do this operation. I want to make sense of that operation in terms of what it really looks like. And for me, if I were to express any fraction, instead of expressing it as a pie or a pizza, I'd expressed as a line that's divided into a certain number of parts. Because in that way, we can find fractions of that line, right? And that's easier to do, to cut up a line than it is to slice things. If you've ever sliced a cake, you'll understand it's not easy, especially if you're greedy. All right, I digress. Now, if we have our fourths here, because I said 2 fourths, that means I'm going to divide my whole into 4 pieces, and each of these pieces is a quarter, 1/4. Yeah. So 2 fourths is this, right? That's this part here, right? No. Can I find a third of this as it is? I could, but it won't be easy to do. Now, what if I were to represent that whole that was divided into 4 parts as something that is divisible by 3? Well, it has to be divisible by 3 and, well, also a multiple of 4, right? So what could we use? What are the multiples of 3 that are divisible by 4? Well, let's go. Let's go through and see if we can find one quickly. We can go 3 times 1. We can go 3 times 2 or 6. We can go 3 times 3, 9. That doesn't work either. We can go 3 fours. And that gives us 12. And that will allow us to get to a conversation when we talk about adding fractions and subtracting later, where we're converting to equivalent fractions. But for right now, with our line model, let me not express this as something divided by these 4 parts, right? Let me express this as something that's divided into 12 parts, right? Where I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 parts. And it happens to be the same length as my whole, which is above it divided into that whole that is above it, that's divided into 4 parts. Lord, help me. Now, when I look at this is 12 parts. If I look at this amount that is equal to 2 quarters, it works out to 1, 2, 3, 4, 5, 6. So this is a 12. This is a 12. This is a 12. All right. Each of those is a 12. But of this total, right, I get 6 12s, which is equal to, we said, 2 quarters. Right. Those of you that understand equivalent fractions are comfortable, but I'm not asking you to do that. I'm just asking you to use your eyes for right now. All right, so we're good, right? No, we want a third of these. Now, if we take a third of these, we can divide this into 3, right? Here and here. Third of this, a third of this is going to give me what? 212. Cool? And that makes sense, right? That's what we expect to have visually, and that's what we have. But more importantly, if I can, let me see whether I can get this done. We can understand the math of it, because a third times 2 over 4, if we can, let me write it down. a third times 2 over 4, the way that we do this is that whenever we're multiplying fractions, we're literally multiplying numerator by numerator and denominator by denominator. There might be situations where you have cancellation, but the fact of the matter is that I'm going 1 times 2 over 3 times 4. So of my 12 parts, two of them, two of that 12 is representative of the initial 1/3 of 2/4. So the answer here is 2 over 12. And the takeaway is that we're going to multiply numerator by numerator and denominator by denominator. That is how that works. All right. Let's look at the last operation, right? We've spoken generally about how we add. Let me just kind of recap that. When we're adding, the important thing is that given the denominators are the same, we can add the numerators. If the denominators are the same and it's a subtraction operation, we can subtract the numerators. That's addition. For multiplication, given our model that we have here, all we're saying is, hey, we can multiply numerator by numerator and denominator by denominator. And we can see that visually in this model here, that it makes sense and it works. Now let's talk about division really quickly. A little bit different, right? Now I have 2/4 here. Same setup. I have my 2/4, quarter, quarter, right? Let me write the rest of my quarter then. Quarter, quarter. Yeah. And I also have my thirds, and a third is going to be larger than a quarter because if I divide something into 4 pieces, that piece is going to be smaller than if I ended up dividing it into 3 pieces, right? Cool. So this is my third, my third, and my third. And I have these two because what I'm looking for is 2/4 divided by 1/3. So essentially, what I want to do is I want to find out how many 1/3 pieces can fit inside 2/4. Now, I can't see that easily if, again, I'm just using fractions that are a quarter in size and a third in size. And of course, these are relative because a quarter itself is saying a piece of a whole. To know the actual size of that whole, that total, oh God, you, you need to have the number itself. That's 100% or the whole, so you know what size that is. But if we make these two lines the same, then we can see that of course a third is going to be longer than a quarter, right? So in order for us to have a proper comparison and to be able to take fractions of one, a number of thirds of one out of the other, I'm going to again represent them as terms into our twelfths, for lack of a better term, right? Because both a quarter and a third can go into 12, or you can get 4 pieces and 3 pieces out of a sum of 12. So what does 2/4 look like as it relates to 12? Well, here is what 2/4 is, right? That looks like 1/2. That looks like 1/12. 1/12 look like 6 pieces, right? Whereas 1/3 here is 4 pieces. Now, how many of these thirds, how many of this can we get out of this? Well, this goes down here. So essentially, if 4 give you a whole here, then in terms of thirds, we're getting how many? We're getting 1.5 or 3 over 2, right? So this is how many thirds we're getting out of quarters. If the 2/4 represents 6/12 and my 1/3 represents 4/12, and how much of this I can get out of this? Well, I can get exactly what, one of it with 2 left over a half, 1.5 or 3 over 2. Now, in terms of the calculation, what that looks like for us is 2/4 divided by 1/3 happens to be the same thing as 2/4 multiplied by the inverse of 1/3, what we call the reciprocal of 1/3. You invert the fraction because right now what when we're looking here, we're saying how much of the thirds fit in here, right? Yeah. This is a size that we're taking. How many one thirds can fit in two quarters? When we multiply, we're saying, hey, in any single unit for a third, there are three pieces. So whatever this number is, if I multiply it by 3, that is how many thirds fit in there. So that's the reason why we invert. We're saying, hey, we're moving from here, the size of the piece when we're dividing, hey, we're dividing by this size. But what we're getting over here when we multiply by 3 is a number because a third, right? 3 thirds are going to be in a whole. So for every whole that you have, oh Lord, you're going to multiply by 3 because that's the number of thirds per one unit, single unit. Should have That's where I should have went with it. God is good. So now that I'm doing this, I know the multiplication process because we just spoke about it. I'm going to multiply top by top and then multiply bottom by bottom. I end up with 2 times 3 or 4 times 1. Jamaican students say nothing. 6 over 4, which happens to be 3 over 2 to simplify, right? We divide through both by 2. All right. This whole exercise was an exercise in understanding the mechanics, right? We're not doing much more than this today. I am going to just kind of summarize quickly if I can. Let me just give us a new page here. We'll summarize real quickly. For addition, if I have two fractions, let's go addition. And this is what we do, right? Given that the denominators are the same, and I should say and subtraction, addition and subtraction, all right? If the denominators are the same, add or subtract numerators and keep denominator. And this is a whole lot of writing to say. If I have 3 over 2 plus 4 over 2 plus 1 over 2, it's the same thing as 3 plus 4 plus 1 over 2, which is the same thing as 8 over 2 or 4, right? Once the numerators are the same, we can add or subtract. That's the important or heavy lifting in this instance, right? Now, for the other two instances, if we can really quickly, for multiplication, multiply numerators or numerator by numerator and denominator by denominator. That's it. For division, invert the term you are dividing by and then multiply. All right. So really basic in terms of the process. You've done this a number of times before. This is not new to you. Just to kind of give you an example of those last two scenarios. If I have 3 over 2 times 5 over 7, and I'm multiplying, I just can multiply across it. So it's going to be 3 times 5 over 2 times 7, 15 over 14. If I had 3 over 2 divided by 5 over 7, we first have to find the reciprocal of 5 over 7, which is just inverting to give us 7 over 5, and then it's business as usual. It's 3 times 7 over 2 times 5, or 21 over 10. All right, or 2 and 110. Gentle people, again, this was just for us to discuss. This is cursory. The next video that we're going to look at is going to be calculation I want you to be comfortable with all the ways these questions can be asked. We're going to definitely look at adding fractions with different denominators, because then we're talking about equivalent fractions. But I just wanted a basic discussion first, kind of preface what we're going to do next. We'll break it up like that. Next time we do the calculations, we'll do all the questions that we can see, hopefully, some good ones. And we'll pick up then and move into other topics. But again, it's just a discussion I wanted to have. So I'm putting that out there. Don't forget to like and subscribe. Thanks for sticking with me, and see you in the next one.